Welcome to a presentation on cost-effective repairs of timber bridges. This presentation covers a multitude of timber bridge topics, but will emphasize several repairs that can be implemented by bridge owners and engineers. This presentation has been prepared for the Minnesota Department of Transportation as part of a study directed towards finding economical solutions for common timber bridge deficiencies. Before specific repair methods are presented, it is important to understand the background and the need which drive the pursuit of cost-effective timber bridge repair methods. The objectives and scope of the project from which this presentation is derived should be understood as well. There are approximately 1,500 timber bridges in the state of Minnesota that, without proper maintenance and repair, will eventually deteriorate to an unusable state. Many of those are on the county or local level road system. Currently, little guidance for repair is provided or available to local level engineers or others whose responsibilities include the management of timber bridge inventories. Numerous research studies have been completed addressing timber preservation and repair, yet not one document specifically addressing Minnesota timber bridge repair exists. Furthermore, the expense of many prescribed repairs is great and often outside the bounds of possibility for townships and municipalities with a lack of available bridge funding. Without the necessary guidance, one is left to devise a solution that could potentially be costly and untested. Solutions for cost-effective timber bridge repairs are needed. This presentation aims to provide cost-effective, easily implemented techniques for timber repair needs more commonly found on timber bridges in the state of Minnesota. More specifically, this presentation intends to help local system engineers in the repair of timber bridge elements. It is anticipated that the guidance and implementation of repair methods presented will improve the overall condition of the transportation system, thus reducing system failures and improving and ensuring the safety of the traveling public. The scope of the investigation from which this presentation is put together had four main foci. 1. Identification of repair strategies through literature searches and surveys that will be effective for Minnesota's timber bridge population. 2. Performance of on-site interviews with local level engineers for additional insight and input. 3. Development of effective repair techniques. And 4. Study of the cost effectiveness and economics of repair strategies and extension of service life. The variety of timber bridge structure types is extensive at the national level, and, as is shown in the figure, even within Minnesota numerous types of timber bridges exist, including slab, stringer multi-beam or girder, girder and floor beam system, truss, arch, and culverts. According to the National Bridge Inventory, these bridges make up a total of 1,503 bridges at the county level. A majority of the bridges, 1,476, are either slab or stringer, multi-beam, or girder. Given that a significant portion of the population lies within these two types, it is here where much of the focus will be in this presentation. Within the National Bridge Inventory, the condition of a bridge is described by its three major components: deck, superstructure, and substructure. A condition rating, 0 through 9, or N if not applicable, is assigned to each component based on its condition when inspected. Each rating is described within the National Bridge Inventory Recording and Coding Guide. The distribution of the condition ratings for deck, superstructure, and substructure among the slab and stringer bridges is shown in this figure. At first glance, it would appear that overall the bridges are in relatively good condition, as the distribution tends to peak around a condition rating of 7, or good condition. At closer look, however, one should note the number of bridges that are considered only in fair or worse condition, that is, rated at a 5 or less. This figure provides the cumulative distribution for each of the bridge elements that fall into or below any given condition rating. For example, 32.1% of all slab and stringer timber bridge substructures are considered fair or worse, a condition rating of 5 or less. Even more, 17.6% are considered to be in poor or worse condition, a condition rating of 4 or less. That is to say that at best, nearly 20% of the substructures have advanced section loss, deterioration, spalling, or scour. Though the deck and superstructure condition ratings tend to be better than that of the substructure, there are still a significant number that require remedial attention. Slab bridges, two examples of which are shown in these pictures, can be identified by the closely spaced nail, spike, or dowel laminated dimension or glue laminated lumber placed in the longitudinal direction of the bridge. The lumber attached in this manner not only makes up the primary superstructure of the bridge, but also the deck. These bridges are most often constructed in panels and then transversely connected using a spreader or distributor beam. Glue-lam panels can come in various sizes, but generally fall in the range of 6 3/4 to 14 1/4 inch deep and 42 inches to 54 inches wide. Even more, sawn lumber can be used in 2-inch or 4-inch widths and 8-inch to 16-inch depths, nailed or spiked together. Span lengths for slab bridges generally do not exceed 36 feet. Douglas fir lumber treated with creosote is the most common material used for the construction of older slab bridges. Stringer bridges can be identified by the full sawn timber or sometimes glue laminated stringers or girders placed in the longitudinal direction of the bridge with a transverse timber deck laid and attached to the top of the stringers. Stringers or girders are commonly 6 to 8 inches wide and 12 to 18 inches deep and spaced 10 to 16 inches apart. Solid sawn bridges generally span lengths of 15 feet to 25 feet, with intermediate supports and multi-spans used for longer crossings. Creosote, or more recently, copper naphthenate, has been used to treat stringers and girders. Glue laminated beams, due to the method by which they are manufactured, have the ability to span much longer crossings than full sawn timber, 20 feet to 80 feet. They are manufactured from 1.5 inch thick construction lumber laminations that are face laminated on their wide dimensions using waterproof structural adhesive. The widths and depths are easily optimized for the span and design loads. The total number of beams is often fewer than that of a full sawn timber bridge construction. Originally, the glue laminated beams were treated with creosote with more recent use of chromate copper arsenate or copper naphthenate. Substructures can take on many forms. However, for timber slab and girder bridges, one of the more common configurations is made up of timber piles, timber pile caps, and timber back walls and wing walls. Two examples are shown in these pictures. The piling are typically Douglas fir or southern yellow pine and treated with creosote. To best determine the level of repair required at any one bridge, a sufficient level of condition assessment should be conducted. A number of tools exist to assist the inspector with the diagnosis of deterioration and needed maintenance. The tools vary considerably in the amount of experience required for reliable interpretation, accuracy in pinpointing a problem, ease of use, and cost. No single test should be relied upon for inspection of timber bridge components. Rather, a standard set of tools should be used by inspectors to ensure conformity in inspections and consistency between inspectors. For the probing and pick test, the use of an awl or other sharp pointed tool can be used to detect soft spots created by decay fungi or insect damage. Probing can locate pockets of decay near the surface of the wood member or can be used to test the splinter pattern of a piece of wood. Non-decayed wood is dense and difficult to penetrate with the probe and results in a fibrous or splintering break. In a fibrous break, splinters are long and separate from the wood surface far from the tool. A splintering break results in numerous splinters directly over the tool. A pick test on non-decayed wood will give an audible sound that one would expect to hear when wood breaks. A pick test on decayed wood will result in a brash or brittle failure across the grain with few, if any, splinters, and the sound will not be as loud. The pick test can subjectively differentiate between sound and decayed wood in weathered specimens that might otherwise be mistaken as decayed under comparable conditions. This simple test does require some experience to reliably interpret the results. Moisture measurements are taken with an electronic handheld moisture meter. The moisture meter consists of two metal pins that are driven into the wood. The meter displays a measurement of electrical resistance between the pins indicating a corresponding moisture content. Moisture content greater than 20% indicates that enough moisture is present for decay to begin. Moisture measurements provide information on areas where water is being trapped, such as joints, and serves as an indicator that a more thorough assessment of an area with high moisture content is necessary. To perform the sounding method, a hammer is used to strike the wood surface. Based on the tone, the inspector might be able to differentiate a hollow sound created by a void or pocket of decay from the tone created by striking sound wood. Some experience is necessary for reliable interpretation of sounding, since many conditions can contribute to variations in sound quality. Sounding is best used in conjunction with other inspection methods. Stress wave devices measure the speed or transmission time at which stress waves travel through a wood member. Stress wave measurements can help locate voids in wood caused by insects, decay fungi, or other physical defects. Stress wave signals are slowed significantly in areas containing deterioration. Because stress wave signals do not distinguish between active decay, voids, ring shakes, or other defects, this method should be used with other inspection methods. The impulse response is determined by coupling the sensors with the timber surface and striking one of the probes to transmit a stress wave through the timber. The resulting time measurement is a reflection of the timber condition. Longer times indicate void spaces, whereas shorter times indicate sound timber. One should note that many piles exhibit splits and cracks, which result in poor acoustic coupling between the transducer and the timber surface, leading to unstable readings. Multiple tests are often conducted at single cross-sections to increase the test reliability. It is possible with severe internal pile deterioration and due to high stress wave attenuation in void spaces that a stress wave travel time measurement may not be obtained. Drill resistance devices record the resistance required to drill through a piece of wood. The amount of resistance is related to the density of the wood in that particular area and can be used to determine if deterioration exists. This method should be used with other inspection tools. The advantage of using drill resistance devices is that the cross-section of the location of drilling can be very accurately defined. Even more, the procedure is minimally invasive and non-destructive due to the small size of the drill bits. Increment core borings of representative areas should be taken perpendicular to the face of the member being sampled. All test holes must be plugged immediately after extracting the increment core with a tight-fitting wood plug treated with a preservative similar in performance to the member being sampled. Increment cores can be visually examined for signs of deterioration and may be submitted to a laboratory for biological and/or chemical analysis. This method is used far less frequently than in the past, since it is somewhat destructive in nature and because the technology of drill resistance devices has greatly improved, providing a reliable, non-destructive method of obtaining the same information as with core boring. Relatively minor maintenance practices, when done routinely, can reduce the need for more extensive repair or rehabilitation. The inherent resiliency of timber can be leveraged with these minor procedures. Maintenance generally falls into one of three main categories: routine maintenance, periodic maintenance, or specific works. Routine maintenance primarily consists of minor reactive type works which are typically expected over the service life, often completed annually, but the precise nature and location are not known in advance. Procedures are generally planned and carried out in a short period of time following identification of need. Periodic maintenance generally occurs at regular intervals of longer than 1 year with the intent of preventing occurrence or progression of deterioration. Unlike routine maintenance, periodic maintenance is most often undertaken on a proactive rather than reactive basis. Specific works include planned and scheduled improvements to the bridge to maintain such things as strength, geometry, and safety. Usually, these maintenance items are scheduled a couple years in advance. The activities of specific works can be similar in scope to repair and rehabilitation activities, and for that reason, the remainder of this chapter will focus on recommended routine and periodic maintenance. Timber bridge preventative maintenance can be completed in many ways. For example, timber construction is generally benefited by controlling exposure to prolonged moisture conditions and treating the end grain of exposed elements. In-place treatments exist that inhibit decay. Additionally, fastener maintenance is key to prolonging the service life of a bridge. With respect to the superstructure, particular attention should be paid to the outside stringers and decks, where exposure to moisture and other elements is most likely. And with respect to the substructure, debris removal and small to medium crack repair are preventative maintenance practices. Each of these areas will be further discussed in the upcoming slides. This section will touch on several general maintenance methods that can help extend the service life of a timber bridge. The simplest preventative maintenance for timber is moisture control. Most commonly, the members subjected to elevated moisture levels are those at or near the ground and/or water line, if at a water crossing such as timber piles. Even so, other bridge elements should be observed for potential moisture problems. Moisture control can be used as an effective technique to extend the service life of many timber elements. When exposure to moisture is reduced, timber will dry to moisture contents below that required for fungus growth and that which is more susceptible to insect inhabitation. For example, generally speaking, timber abutments placed up and away from stream banks have an extended service life compared to elements near the stream that are repeatedly subjected to wet and dry cycles. Since it is highly unlikely abutment and pile locations will be moved on existing bridges, it is paramount to take note of particular piles that are apt to see the wet and dry cycling so that special attention may be paid to these piles. Without preventative measures, the ends of timber members are more susceptible to draw in water than other portions of the member. If the end has been cut, a timber treatment should be brushed on, and where exposed, should be capped with flashing such as tin, aluminum, or similar material, with minimization of water exposure being the goal. In-place treatments are another common preventative maintenance technique applied to timber elements. Surface treatments, paste, and fumigants are three types of in-place treatment that are frequently used. On-site fabrication of timber bridge components typically results in breaks in the protective plant-applied preservative barrier. Pile tops, which are typically cut to length after installation, specifically need reapplication of an in-place preservative to the cut ends. Likewise, the exposed end grain and joints, which is more susceptible to moisture absorption, and the immediate area around all fasteners, including drill holes, require supplemental on-site treatment. Periodic inspections should seek to identify cracks, splits, and checks that result from normal seasoning, as well as areas of high moisture or exposed end grain and joint areas. These areas require periodic reapplication of a supplemental preservative. The condition of all structural fasteners should be checked for corrosion and tightness. Fasteners should be retightened to a snug tight condition if deemed loose. Where significant corrosion is present, fasteners should be replaced altogether. This next section will focus on specific maintenance methods for superstructure elements. The outside stringer on a timber bridge is more susceptible to deterioration due to its increased exposure to the elements including rain, sunlight, and debris flow. All dirt and loose, decayed material should be removed and consideration given to adding flashing to prevent excessive wetting and further repairs if checks and splits are present. Timber decks can be susceptible to vegetation growth as gaps between deck boards are quite common. These gaps fill with dirt and gravel that in turn create an environment in which vegetation can begin to grow. Vegetation growth is a clear indicator that debris has collected and water is being retained within the gaps. As such, the vegetation and debris should be cleared to prevent deterioration of the deck. This next section will focus on specific maintenance methods for substructure elements. Commonly, gaps between deck boards on timber bridge decks form and allow at least a nominal amount of debris to pass through. The debris is able to collect on top of pile caps, which can trap water against the pile cap. Due to the retained moisture, deterioration of the pile cap advances at a quicker rate than would otherwise occur. If left alone, the pile cap could deteriorate to a point where sufficient support of the superstructure is compromised and complete replacement of the pile cap is necessary. Debris should be cleared or washed from the top side of the pile caps to reduce chances of water retention. Small to medium cracks and splits caused by weathering or shrinkage create pathways for decay fungi to enter the untreated wood at the core of the timber pile. Therefore, consideration should be given to regularly repairing cracks and splits. Epoxy grout can be injected under pressure for filling checks and splits. The epoxy seals the affected area, preventing water and other debris from entering. It can also restore the bond between separated sections, increase shear capacity, and reduce further splitting. Another method involves injecting low viscosity epoxy to fill the void, then sealing using a sealing epoxy. For several reasons, there may be a need to repair a deteriorated or decayed laminated bridge deck. By nature of the construction method, this repair can seem daunting. The following slides present one method for repairing localized areas of decay within these decks. The method presented is used for repairing a dowel or spike laminated deck, commonly called a wheeler deck, like that shown in the photos. One which has a localized area or areas of deterioration extending to either partial depth or full depth. Due to the strength of the repair, it is recommended that the area of repair be no longer than 5 feet and no wider than 3 feet. Some of the materials and tools necessary to complete this repair include a circular saw, awl, and drill, timber surface treatment, plywood or sheet metal, concrete or non-shrink grout, epoxy-coated reinforcement, galvanized lag bolts, a short, lightweight steel beam, and epoxy polymer and construction adhesive approved by the county engineer. To begin this repair method, the areas and extent of deterioration must be identified by sounding with a hammer, using an awl, or any of the advanced inspection methods. Next, using a circular saw, cut to the depth of deterioration, either full depth or partial depth. Be aware that additional tools may be needed at spike locations in spike laminated decks. Deteriorated timber should be removed with hand tools such as hammers and chisels, or small power tools to avoid inflicting damage on remaining sound timber. Once exposed, the remaining timber should be treated with a surface treatment to prevent future deterioration. After the deteriorated material is removed, the resulting hole should be approximately rectangular in shape with sloped sides at the longitudinal ends. For partial depth small repairs, galvanized lag bolts sufficiently sized to hold the repair material need to be installed into pre-drilled holes in a welded wire reinforcement mat cut to size placed within the repair area and wire tied to the lag bolts. For full depth repairs, holes should be over-drilled in the remaining sound material to accept both ends of the rebar and rebar adhered in place with an approved construction adhesive. Using a sufficient number of common deck screws, affix a piece of plywood or sheet metal to the underside of the deck to serve as formwork. For obvious reasons, a partial depth repair does not require this step. For longer deteriorated areas, it may be necessary to attach a structural beam which has been properly sized along the length of the opening, in addition to the repair steps already described. In any case, a beam would be helpful to provide additional support and strength for little additional cost. Complete the repair by filling the hole with a fiber-reinforced concrete mix proper for the final bar spacing, clear spacing, durability, etc. Trowel finish the top surface even with the adjoining timber deck and roughen to appropriate levels to provide sufficient skid resistance. Once cured for the time commensurate with the selected concrete mix and placement conditions, the formwork may be removed from the underside of the laminated deck or simply left in place. It is not uncommon for individual stringers to need repair. This could be the result of overloading, exposure to moisture, debris impacts, or other. The following slides present a few methods by which these stringers can be repaired. These repair methods are used for strengthening timber stringers or girders, like those shown, that have localized minor to moderate deterioration that has weakened the overall strength of the member at the ends or along the span by attaching steel or timber members to timber stringers or girders using through bolts or lag bolts. Some of the materials and tools needed to complete the repairs include galvanized threaded rods or lag bolts, steel channels, plates or angles, drills, and socket wrenches. The first step to this repair is to determine the required capacity of the stringers or girders per the codified specifications. Based on the level of deterioration and remaining sound portions, estimate the remaining capacity. Knowing the required strength per the design specifications, the additional strength required can be calculated. To increase the shear capacity at the end of the beam, size timber fish plates, steel plates, or channels to be added to each side of the stringer that will increase the shear capacity to that which is required. Similarly, to increase the flexural strength of the positive moment region, if only additional tensile strength is required, timber fish plates, steel plates, or angles may be used. If additional tensile and compressive strength is required, top and bottom angles or channels added to each side may be used like that shown here. Once the configuration has been selected, size the elements so that the composite member capacity meets or exceeds the required capacity. It is recommended that all added elements extend a minimum of 24 inches to either side of the deteriorated area where possible. Per the national design standards, size and space the through rods or lag bolts to sufficiently anchor and attach the channels to the stringer to ensure the desired composite action. To simplify construction, lag bolts rather than through rods are recommended. The construction procedure begins by using awls or other non-destructive methods to identify the area and extent of deterioration. Using the steel elements that have been properly sized for the desired added strength and also for the recommended minimum extension of 24 inches to either side of the deterioration extents, center the elements on the area of deterioration. Attach the pre-drilled elements to the stringer using threaded rods extending through the stringer and elements on each side or individually using lag bolts. Pattern the rods or bolts per the design layout. Additional holes for drainage in any members fastened to the bottom should be provided. Timber piles are often the bridge element that most quickly and frequently deteriorates. The more likely exposure to moisture and cycling of wet and dry periods promotes deterioration at a more rapid rate than other elements. Where the pile has experienced localized deterioration, the addition of steel channels to the piles can provide the additional strength needed. This method is used for strengthening timber piles that have localized minor to moderate deterioration or damage no longer than 18 inches that has weakened the overall strength of the member. Some of the materials and tools required for this method include lag bolts or threaded rods, steel channels, and wood preservative. The first step in the process is to determine the required capacity of the pile per codified specifications. Then estimate the remaining capacity of the pile based on the sound portions of the pile cross-section and calculate the additional capacity required. Size the steel channels to be placed on opposite sides of the pile that will increase the capacity to that which is required. It is recommended that the channel extend a minimum of 24 inches beyond the deteriorated section on either side. Per the National Design Standard, size and space the lag bolts to sufficiently anchor and attach the channels to the pile to ensure the desired composite action. To simplify construction, lag bolts rather than threaded through rods are recommended. Weld 1 by 1 by 1/8 inch angles to the web of the channel, equally spaced between rows of bolts. The angle acts as a cleat to better engage the pile and channel. Notch the pile to accept the welded cleats and so that the channel web lies against the face of the pile. Where the pile has been trimmed and notched, apply a preservative treatment to help protect the pile going forward. Finally, attach the pre-drilled channels to the pile per the designed lag bolt or threaded rod pattern. One method successfully employed to strengthen deteriorated piles is to encase the pile in a reinforced concrete jacket. This section will provide the steps necessary to complete this method. This method is used for strengthening timber piles that have localized minor to moderate deterioration or damage no longer than 18 inches that has weakened the overall strength of the member. Some of the materials and tools required to complete this repair include corrugated metal pipe, steel cable, lag bolts, reinforcing bars, concrete, and a metal nibbler or saw with metal cutting blade. The procedure begins with determining the required capacity of the pile per codified specifications. Then an estimate should be made of the remaining capacity of the pile based on the sound portions of the pile cross-section. The capacity could be conservatively assumed to be 0 since there will no longer be the ability to inspect the pile once the repair has been completed. After, calculate the additional capacity required. Determine the length of pile cast required. This repair can encapsulate the entire pile or shorter portions like that seen in this photo. Determine the diameter of corrugated metal pipe, or CMP, required. A 6-inch nominal thickness of encasing concrete is recommended. For example, a 24-inch CMP for a 12-inch diameter pile. The construction procedure begins with identifying the area and extent of deterioration or damage using awls and/or other non-destructive methods. If near the ground surface, remove surrounding soil to a depth of 18 inches below the extent of the deterioration. Install lag bolts into the pile radially at quarter points. Space the bolts longitudinally at a maximum of 24 inches on center. The bolts are used as standoffs for the longitudinal reinforcement bar, which is recommended to be spaced midway between the pile and the CMP with a minimum of 2 inches cover. Then attach the longitudinal reinforcement bars to the bolts with wire ties. Beginning at one end of the pile, spirally wrap the steel cable around the longitudinal reinforcement. Split the CMP into 2 halves with a metal nibbler, grinder with cutting wheel, or saw with a metal cutting blade. Alternatively, CMP can be purchased in 2 halves, which would eliminate this step in the procedure. Place the 2 halves around the pile and attach together using steel banding, double angles and bolts, or other means. Depending on the location of the deterioration or damage, the CMP may rest on the ground below, which acts as a form for the bottom of the cast. A means for holding the CMP in place prior to and during filling should be devised. To complete the repair, fill the form with concrete and create a sloped top edge to allow water to shed away from the pile. Occasionally, multiple piles within a group, whether it be in a pier or abutment group, require repair. Collectively, these deteriorated piles can decrease the pile group's strength below that of a safe carrying capacity. One method to bolster the entire group is to encapsulate the group in reinforced concrete. The following slides provide the steps necessary to complete this method. This method is used for strengthening a group of timber piles in a single pile bent that have localized minor to moderate deterioration or damage that has weakened the overall strength of the bent. Some of the materials and tools required to complete this repair include lag bolts, reinforcing bars, concrete, and formwork. The procedure begins by excavating a minimum of 12 inches below the area of deterioration or damage, or at the ground surface of the pile group, whichever is lower. If piles are submerged, a cofferdam structure will be needed and the site dewatered. Add reinforcement bars for shear transfer by drilling holes through the pile and epoxying into place. Install lag bolts along the face of the pile to serve as standoffs for the reinforcement bars that span from pile to pile. Next, place the longitudinal and shear reinforcement around the pile group. Construct formwork for the reinforced concrete. Finally, place concrete around all piles and ensure the top surface slopes away from the piles to properly shed water. Cost estimates for each of the previously described repairs are provided in the following slides. One should keep in mind that each bridge repair is unique and that the cost estimates may not always be accurate. Even so, the estimates should give a good approximation for those seeking a ballpark figure for each repair. The estimates were completed using general assumptions based on the repair details and experienced Minnesota union labor. Where the work is self-performed, a 25% savings is anticipated based on labor experience and availability of equipment and materials. For the repair of laminated bridge decks, a partial depth repair is estimated to be in the range of $263 per square foot to $329 per square foot. A full depth repair is estimated to be in the range of $420 per square foot to $449 per square foot. The smaller and larger amounts reflect larger and smaller repairs, respectively. In each case, additional costs for traffic control or a bridge closure will need to be added, along with approximately $250 per day for mobilization. Also, in the case of a full-depth repair, the cost may be increased by the height of deck and/or water depth dictating the equipment required. For the strengthening of individual timber stringers where additional shear reinforcement is required, the cost is estimated to be $1,500 for each stringer repaired. The cost of mobilization, estimated at approximately $250 per day, is in addition to that estimate. One should also note that the cost of repair may increase depending on the bridge height and water depth dictating the equipment required. For the strengthening of individual timber stringers where additional flexural reinforcement is required, the cost is estimated to be $3,000 for each stringer repaired. Again, the cost of mobilization, estimated at approximately $250 per day, is in addition to that estimate, and the cost of repair may increase depending on the bridge height and water depth dictating the equipment required. This estimate assumes a 9-foot repair length. To complete the addition of steel channels to piles, the cost is estimated at $1,940 per pile, with additional mobilization costs of $250 per day. Any dewatering costs that might be incurred are not included in this estimate. For the addition of concrete jackets to piles, the cost is estimated at $5,520 per pile, plus or minus $370 per foot variance from 15 linear feet. The mobilization costs of approximately $250 per day and any dewatering costs that might be incurred are not included in this estimate. For encapsulation of pile groups, the cost is estimated to be $16,400 per pile group plus $450 per linear foot over 28 feet in length. The mobilization costs are estimated to be $400 per day, and approximately $6,500 should be added for any necessary cofferdam and dewatering. An assessment of the economic impact one might expect by repairing timber bridges in Minnesota should be completed to ensure that funds are being spent in an optimal manner. The economic impact of the repair techniques as they extend the service life of Minnesota timber bridges can be assessed in a couple of ways. Often the direct costs of the repair are only directly compared to the cost of replacement or delay thereof. This is most common because the costs are most easily quantified. Another method is to, in addition to the assessment just described, quantify the cost of a detour should a bridge be posted or closed altogether. Though the costs to the public or societal costs are not directly the cost of the bridge owner agency, they are costs nonetheless that are carried by someone, for example, cargo carriers, the agricultural industry, or the like. It is when these indirect costs are incorporated into the overall cost, direct plus indirect, that the benefits of repairing or reconstructing a bridge are quickly realized. Per the 2012 National Bridge Inventory, 1,504 bridges in Minnesota were classified as timber bridges. Of these bridges, 1,067 were not load posted and 406 were load posted, while the remaining number were either unknown, closed, or posted for another restriction. This table presents some of the additional key metrics for the posted and non-posted bridges that will be important to the economic assessment of completing repairs. A quick look at the metrics would suggest that a significant number of bridges will require posting over the next 10 years if left unmaintained. The average age of the posted bridges is 52 years old, while the average age of the non-posted bridges is 42 years old, only 10 years younger. Even more, the sufficiency rating drops 20 percentage points and the average posting evaluation decreases 3 points between the two groups. basis for the posting evaluation score is further described in this table. One can see the range is 0 to 5 and is a function of the relationship of the operating rating and maximum legal load. Quite simply, the less load the bridge is able to safely support, the lower the score. To reiterate, the average posting evaluation decreased to 3 points between the two groups from 3.95 to 1.94 for the non-posted and posted bridges respectively. This means that, on average, the maximum legal load is nearly 30% less than the operating rating load for posted bridges. For the purpose of the economic assessment, a 75-year life cycle was assumed. This assumption is based on the current age distribution plot shown in this figure, where at or around 75 years the number of bridges exceeding that age is significantly reduced for both non-posted and posted bridges. The direct costs of reconstruction and repair are calculated in terms of net present value. The cost of reconstruction from the present year to the end of its assumed service life at 75 years is compared to the cost of repair occurring in the present year or any year thereafter to the end of its assumed service life of 75 years, plus the cost of reconstruction at an extended service life age of 85 years. An added service life of 10 years was conservatively assumed for the sake of this assessment. It is believed that any specific repair previously prescribed will have a service life beyond that which has been assumed. An escalator of 6% per year was added to the repair cost, which quantifies the continued degradation of the bridge structure and the cost of delaying repairs. As an example, this figure presents the net present value reconstruction cost of a $50,000 bridge compared to the net present value repair and reconstruction costs at each of the varying repair cost levels. At the $20,000 repair level, for an average aged posted bridge, which is 50 years, it would be more economical to complete the repairs within the first 7 to 8 years, or at age 57 or 58. It is at this point in time that reconstructing the bridge becomes more economical than repairing the bridge for $20,000 and replacing the bridge for $50,000 at age 85. This scenario is designated by the bold curves. As an additional example, a similar scenario is presented in this figure for an average age $50,000 non-posted bridge. In this case, it would be more economical to complete the repairs within the first 10 or 11 years, or at age 50 or 51. As might be expected, the more a bridge costs to reconstruct, the more economical conducting repairs becomes even at later ages. Conversely, a bridge with relatively low reconstruction costs might need to be repaired earlier rather than later for repairs to be an economical pursuit, especially for more expensive repairs. What's less obvious is a precise timeline when a decision for repairs in lieu of reconstruction is most economical. It is important to note that a series of these graphs have been developed for various bridge reconstruction and repair cost scenarios and included in the final report for this project. They aim to assist an engineer with identifying when the economical turning point is for repairs or reconstruction. Though indirect or societal costs are not directly paid out by the bridge owner nor any one entity or individual, the costs are borne by the bridge users collectively. The cost of an extended detour due to bridge closure or posting can quickly add up and thus should be considered in the overall decision to repair or reconstruct a bridge. Passenger vehicles aside, the cost of detouring trucks alone for extended periods of time can quickly add up. To quantify truck detour costs, a tool was developed by Iowa State University to assess the impacts of out-of-distance travel for single-unit and combination trucks. Numerous variables impacting the economic assessment are included in the overall equation. Accordingly, several simplifying assumptions had to be made, though each is soundly based on previously completed research. This table provides the truck operation costs for single-unit and combination trucks. In addition to the truck operation baseline costs, which include fuel, maintenance and repair, tires and depreciation, other costs factor into the overall cost. These include the costs associated with additional increment of travel such as congestion, crashes, air and noise pollution, the cost for stop-start driving conditions, and the driver pay and roadway usage. This figure presents the net present value for truck travel cost in the event of a bridge closure or posting over the duration of the assumed remaining service life, which is 75 years, for an average aged posted and non-posted bridge. Referring to the table immediately preceding this slide, the total number of trucks, single unit plus combination, was derived from the average ADT and truck percentage. The information gathered does not differentiate the types of trucks crossing bridges, so it was assumed to be a 50-50 ratio of each type. For the purposes of this assessment, the number of trucks is considered to be unchanging over time. It is clear by observing the increasing user cost over time that when coupled with the direct cost of bridge repair or reconstruction, the overall costs are minimized by keeping a bridge unposted, whether it be by repairs or reconstruction. Simplified cash flow diagrams are presented here for some of the potential scenarios for an average age timber bridge. The first, shown at the top, represents an average non-posted bridge at age 40. At around 50 years of age, the bridge requires posting, thereby incurring user costs due to the required detour. Several years later, the bridge is repaired, thereby removing the posting and eliminating user costs from a resulting detour, and also extending the service life to 85 years, at which time the bridge is reconstructed. The second, shown second from the top, represents an average non-posted bridge at age 40. At around 50 years of age, the bridge requires posting, thereby user costs are incurred due to the required detour. The bridge goes unrepaired for the duration of the service life, ending at 75 years, at which time the bridge is reconstructed. The third, shown second from the bottom, represents an average posted bridge at age 50. User costs are incurred until a repair is completed. This repair eliminates the posting and thus the user costs from an associated detour and extends the service life until age 85, at which time the bridge is reconstructed. The fourth, shown at the bottom, is much like the previous example and represents an average posted bridge at age 50. Since the bridge is already posted, user costs are incurred each year until the bridge is reconstructed at age 75. To briefly summarize the economic impact of timber bridge repairs, two important points should be reiterated. The first is that if only direct costs of reconstruction or repair are being considered, there is a point in time when the decision to repair or to reconstruct makes most economical sense, and this point in time can be closely defined when knowing the costs associated with each. Secondly, when indirect costs are considered, it almost always makes most economical sense to prevent or eliminate posted bridges, whether it be through repair or reconstruction. This brings us to the end of this presentation, which introduced several cost-effective, easily implemented techniques to help local system engineers in the repair of timber bridge elements. With the implementation of the repair methods, it is anticipated that timber bridge service life will be extended, thus reducing system failures and improving and ensuring the safety of the traveling public. Several agencies should be acknowledged for their participation in conducting this study. They include the Minnesota DOT State Aid and Bridges Offices, the Minnesota Local Road Research Board, the University of Minnesota Duluth Natural Resources Research Institute, the Iowa Highway Research Board, Iowa State University Bridge Engineering Center, and HDR. For additional information, please feel free to contact Justin Dahlberg or Travis Hosting at the Bridge Engineering Center at Iowa State University.